In this day and age, it seems like every single day we open up our news apps and look at the headlines, we see a new news bulletin about how Vladimir Putin is once again threatening the Western nations of the world with use of nuclear weapons and tactical nuclear weapons. It seems like everybody is talking about nuclear energy and power, from the use of nuclear weapons in Russia's war on Ukraine to the use of nuclear power in potentially combating the woes of climate change and driving us towards a more sustainable future. But what exactly is nuclear power, and what exactly are nuclear weapons, and how do they work? And why does the world go so crazy for nuclear energy? Well, stay tuned and let's talk about the science behind that.
Welcome to The Science Behind That with Atticus Hamilton.
Hello all you scientists, and welcome on back to the Science Behind That podcast. I hope you guys are doing good, and as you heard in the intro, today, ladies and gentlemen, we are going to be talking about the science behind nuclear energy and nuclear power. Along with that, we're also going to be talking about the science behind nuclear bombs, and other types of nuclear weapons. So, ladies and gentlemen, I hope you enjoyed today's episode. It's going to be a little longer than previous ones. I hope you guys are okay with that. It's going to be a dope episode. So, before we jump in, ladies and gentlemen, go grab yourselves a nice steaming hot cup of coffee, add a little bit of maple syrup to it, and let's jump right in. So, nuclear energy and nuclear bombs. A very loaded topic, of course, these days in the world today. This is becoming an ever more apparent topic of conversation, it's an issue in terms of nuclear warfare that unfortunately is seemingly coming up again in our world, despite the fact that we narrowly avoided nuclear war in the Cold War. But despite that, nuclear power does genuinely provide us, along with geothermal, the best way to solve our energy crisis around the world. Nuclear power, nuclear fusion in particular, presents us the potential to have near unlimited energy with no toxic byproduct, no greenhouse gases, no radioactivity, none of that. And hopefully, I'd like to hope that one day my children are going to grow up in a world where the bulk of our power infrastructure is generated from nuclear fusion, geothermal, and hydrogen fuel cells. Now, whether or not that will become reality is an entirely different question, but I really hope it does. But that's why nuclear energy is important. And before we can understand nuclear energy, let alone nuclear bombs, or the process of uranium enrichment, we need to first understand the basic building block of all matter in the universe, which is the atom. So, an atom, as we all learned from general chemistry, is the basic subunit, if you will, of all matter. While that technically is not accurate 100%, it is fairly accurate. So, an atom is generally composed of a nucleus and then electrons around it in regions of electron density. That nucleus, depending on the atom, is going to have a variable number of protons and neutrons, which are just even smaller particles that make up a single atom. Now, we have visualized atoms, particularly iron and copper atoms, with the use of electron microscopy. Generally speaking, an atom will be composed of relatively equal parts protons to neutrons, and then we'll have the electrons orbiting around it. And for the longest time, people thought that electrons orbited around the nucleus, which is the center of the atom, like stars or like planets around a star, but that is not accurate. So in fact, electrons sort of, they're found in regions of electron density around atoms, and these are called orbitals. So there's 4 different types of electron orbitals. There's s orbitals, p orbitals, d orbitals, and f orbitals. And they all look slightly different. If you're curious, if you want to learn more about this in particular, this area of chemistry in particular, I definitely encourage you to go to periodictable.com. It has a nice little visualization of that. But ultimately, within each one of these orbitals, an electron may be found, and these orbitals contribute to bonding of atoms to one another. Now, is this really relevant for what we're discussing today? No. But what is relevant is the structure of atoms being protons and neutrons. So if we take uranium, for example, uranium-235, which is generally the most common isotope of uranium, has 92 protons and 143 neutrons for a total molecular weight of 235. Now, this leads us into nuclear fission, because the question is, well, Atticus, how does a nuclear reactor work? Very simply, by splitting these up. So, and this is a nuclear fission reactor, mind you. So, the way a nuclear fission reactor works is, in its most basic sense, it breaks in half almost, and it's not generally in half, but it breaks up atoms. And so in this case, the 92 protons and 143 neutrons, it would break that atom in half, and then that would release heat and other forms of radiation like X-rays and beta particles and alpha particles, and of course free neutrons. So how does a commercial level nuclear fission reactor work then? Well, generally it's just a big steam generator. So for the most part, most of our ways of generating electricity involve turning an alternator or an alternator-like device to generate electrical current. And in the event of nuclear fission reactors, they're no different. So basically, if you imagine those like hourglass-shaped white smokestacks you see like on any climate change video or documentary or anything, those are nuclear reactors. And the white smoke coming out the top isn't carbon dioxide or methane or anything like that. It's just simply water vapor. And so the way this works is, in the deepest part of the nuclear reactor, you have the core. And in the core of the nuclear reactor, you have your rods of enriched uranium. Generally, it's enriched uranium-235. Now, theoretically, you could do it with like plutonium, but for the most part, it is enriched uranium-235. And so you have these rods of uranium that make up the central core of the reactor. And within the core, the outside, or it's lined by what's called a casing. Now, the casing is generally going to be made up of lead and other materials, other metals that are able to both shield the radiation but conduct heat pretty well. And so the casing surrounds this core of those reactor rods, and then on the outside of that casing, you essentially have coils of tubes that surround it, and these coils of tubes contain water. And so as you split the atoms in half, inside these reactor rods, it generates heat, right? Well, this is a lot of heat that it generates. And so this heat heats up the outer casing, which then in turn heats up the coils of water, and that causes the water to instantly evaporate. Goes up the coils and through a turbine. And the steam pushes through the turbine, spinning the turbine, generating electricity. In the same way that at a hydroelectric dam, water going through the dam output turns a turbine and generates electricity, this generates electricity. Coal-fired power plants, gas power plants, they all work in geothermal. They all work in a very, very similar way, which is heating up either water or some other fluid like refrigerant to evaporate it, which will then spin a turbine. And nuclear fission is no different. And as I said, it produces a lot of heat. And how much electricity does it produce? Well, the total binding energy released from a fission reaction varies depending on the atomic nucleus, but averages around 200 megavolts for uranium-235, or 3.2 times 10 to the negative 11 joules, which is about 82 terajoules per kilogram. That is a lot of energy. And to put that into perspective, natural gas energy creates around 35 megajoules per cubic meter, which is even less energy, because 85 terajoules is around 85 million megajoules of energy per kilogram, whereas natural gas produces an energy, or has an energy content of around 35 to 39 megajoules per cubic meter. So obviously nuclear fission is the way to go in terms of energy production. But what are the byproducts of a fission reaction? Well, unfortunately, this is where it becomes a problem, right? Because the byproducts of a modern nuclear fission reactor are radioactive isotopes such as iodine-131, cesium-137, and strontium-90. And these are all created in the process of splitting the uranium atom into parts, because the more you split the atom into parts, it basically synthesizes lighter and lighter elements, which are also radioactive. Because all radioactivity is it's basically unstableness. So radioactivity is basically when an element or an atom is unstable in its current proton, neutron, and electron configuration. And as a result, it either has protons or neutrons sort of beaming off of it at a relatively constant pace, and that's radioactivity. Those are your alpha and beta particles that these radioactive atoms emit as they're slowly breaking down into non-radioactive forms. And that's nuclear fission. So what about nuclear fusion? Because there's two types of nuclear reactions, fission and fusion. And fusion is, in my opinion, the key to a long-term energy source without this radioactive byproduct. So, what is nuclear fusion? Well, very simply, nuclear fusion it's still a nuclear reaction, but instead of splitting an atom in half, you're actually just smashing two atoms into one another to create the next level of element. And that also generates a lot of heat. And in fact, if we compare modern fusion deuterium reactors to modern uranium fission reactors, in terms of per kilogram weight, fusion deuterium reactors produce around 4.4 times more energy than fission reactors. However, to get to that level of energy production, you need a lot of input energy and a lot of deuterium. So what is deuterium? Well, deuterium is an isotope of hydrogen. So there's three isotopes of hydrogen. You have protium, deuterium, and tritium. And protium is just one proton and no neutron and one electron. Deuterium is a proton and a neutron. And tritium is a proton and two neutrons and an electron, of course. Now, tritium is radioactive, but it's nowhere near as radioactive as uranium is, or iodine 131, or cesium 137, is not radioactive. And I mean, it is radioactive, but it's not radioactive on that same level. And so all a fusion reactor does, basically, the modern fusion reactors it's basically a big particle accelerator. So it's a cylindrical track that heats up to very, very hot temperatures, around 300 million degrees. And it accelerates a deuterium atom and a tritium atom, and it smashes the two of them into one another. And then the byproduct produces a ton of energy, and no radioactive byproduct. Now the goal is to do this reaction with 2 deuterium, right? This is called a DD system compared to a DT system. Now a DD system is generally better than a DT system. However, DT fuel requires less temperature, whereas DD fuel requires higher temperature. And additionally, the other issue that people have been running into with fusion reactions is, how do you contain the reaction, right? Because with fission, it's pretty easy to contain, because you just put it inside of a casing that is insulated against the radioactivity, particularly the neutrons. And once you split one of the uranium atoms, that will release neutrons that will then go in a controlled reaction, then splice the other atoms within the other cores of uranium. That doesn't necessarily happen with fusion. And so you need methods to keep the reactant material in one place, and also so that temperature doesn't melt the inside of your reactor. So how did scientists do this? Because there are nuclear fusion reactors in development as we speak, some in the US, one in Japan, and one in Australia. They pretty much used X-rays. They used X-rays and a strong electrical current to generate plasma and X-rays that contains the reaction to a very narrow space within the reactor, which then allows for the generation of electricity, heat, which then heats up water or refrigerant and then evaporates through the turbine and creates electricity. Same way as fission. The only difference is how we're generating that heat, and in fusion it's from smashing deuterium into tritium. And of course, those physicists in the audience are going to say, well, I guess this was a very, very simplified explanation. It was, because I could go all day on this topic, and frankly, there are classes in college and in grad school that spend an entire year on this topic. So it's a very dense topic, but in essence, that's the difference between nuclear fission and fusion. And nuclear fusion does not produce radioactivity. So it does, if we can get the economics of it down, it does present the potential for almost unlimited energy. And then, ladies and gentlemen, this leads us into the other part here, which is nuclear bombs, right? So I think when we talk about nuclear power, that's the big thing that everybody is worried about, right? Is nuclear bombs. So basically, you have 2 types of nuclear bombs, a fission bomb and a fusion bomb. A fusion bomb is also called a hydrogen bomb. And we do have examples in history of hydrogen bombs being detonated, such as the Tsar Bomba, which was the largest nuclear weapon ever developed in the history of mankind. And we're going to get into how fusion bombs work, but of course we have to talk about fission, and of course before we can do that, how do you get uranium in the first place, right? So we're going to talk about the actual process of enrichment of uranium. So FBI, if you're listening to this episode, yeah, I did look up how to enrich uranium, and it is just for this episode. So yeah, I'm glad we're cool. So there's a couple different ways to enrich uranium. Generally in the environment, the go-to isotope for both reactor cores and weapons cores is uranium-235. And in the environment, in uranium ore, it constitutes about 0.7% of uranium ore. And then for commercial reactors, it's enriched to around 3 to 5%. And then for nuclear bombs, we're talking 30 to even higher percentages enrichment for bombs. So that's the difference between bomb-grade uranium and like reactor-grade uranium is the percent composition of core that is uranium. So how do we enrich uranium? There's a couple different ways. You could do gaseous diffusion, gaseous centrifugation, and laser separation. So we're going to be mainly talking here about gas centrifuge and laser separation, just because those are the more modern ways to do it. And generally, when it comes to like international terrorist organizations or hostile countries like North Korea or Iran, when it comes to the development of nuclear bombs and nuclear reactors, it's a process of enrichment that is one of the most difficult aspects. So I'm going to try and keep my explanation simple. In the event that I highly doubt it, but in the event that North Korea or Iran is listening to me. So how does a gas centrifuge work? Well, pretty simply. So a gas centrifuge is just a big centrifuge. It has a chamber with a spinning electric motor and a rotor and a casing to insulate the radioactivity. And basically what you do is you input gaseous molecules of UF6, which contains uranium-238 atoms, and then gaseous molecules of U-235, which is the go-to, right? And so generally, what type of form is this gas in? So usually it is in the form of uranium hexafluoride. And so you pump this into the centrifuge, and all that happens is it spins. The inside of it spins, and because uranium-238 is denser, it sinks to the bottom, and uranium-235 is lighter, so it stays more towards the middle or the top. And then the gas that's in the middle or top is piped off from that centrifuge into another centrifuge where it's spun down again, and then it's pumped back into the old one, and so on and so forth. And this process repeats, and this is at high temperatures, right? To get gaseous uranium, this is at high temperatures, and then this process goes back and forth basically as it's slightly enriched. So this continues until the uranium is at an enriched level, and then the gas is condensed back down into a liquid state. And then from there you can develop a core. And these centrifuges are connected in a train, basically, which is just one centrifuge after the other, after the other, after the other. So the different gases of U-235 and U-238 can flow freely from one chamber to the other. And that is the go-to process, at least here in the United States for the most part, where most commercial uranium, or of how most commercial uranium is enriched. And then laser separation is pretty new. So laser separation involves three main systems, which is the laser, the optical system, and the separation module. And so these lasers are developed to photoionize a specific isotope while not affecting another isotope. And that affected species is chemically changed, which allows that material to be separated from the heterogeneous mixture that it's in. And then it uses generally a uranium metal alloy, the laser separation tech, to feed the material through. And it uses the UF6 or the uranium-238 as your feed material. And so basically it's more complicated. Honestly, it's a more complicated way of doing it, but it requires less space and it could theoretically be done faster because you don't need to chain link centrifuges to gaseous centrifuges together to, isolate the uranium. And that's how uranium is enriched, right? So now you have, we talked about reactors. So the reactors get the 3 to 5% enriched uranium, right? So now you have like 50% enriched or higher uranium cores for bombs, right? So how does a fission bomb work then? A fission bomb is basically a nuclear reactor that's designed to expend the entire payload of core in one reaction. So nuclear reactors, so fission reactors don't do this. They slowly use neutrons to break up individual uranium atoms at a time, which then creates a very controlled cascading reaction of the neutrons that are released from the process of splitting those atoms, splitting more atoms, and so on and so forth. It's very controlled. Now, the way a nuclear fission bomb works is basically the atoms are just split into smaller and smaller nuclei using a charge, using some sort of conventional detonator to make this occur. And usually this happens instantaneously, where it causes the entire warhead core to split, basically. And again, a neutron is going to be shot at the nucleus, causing the instability and fusion. And you can also mix uranium and plutonium for nuclear fission warheads, etc. And then this causes a chain reaction, and it causes the bomb to explode, which is why when we see nuclear meltdowns, which is because the cores aren't being cooled down enough from incoming water, so they overheat and get to too high of temperatures and melt through the chamber. This is why we don't see nuclear explosions in reactors when they undergo a meltdown, because the mechanism, while it is very similar, it's different. We're not splitting the cores in a nuclear reactor all at once like we are in a nuclear fission bomb. So then how does a fusion bomb work? A fusion bomb is very, very easy to understand. A fusion bomb basically uses a fission bomb depth charge almost. It uses a primary charge, which is a fission bomb, to generate enough heat to then cause a fusion reaction, which generates more heat. Exact same way as a fusion reactor works, except the way you're generating the initial amount of heat to cause that fusion reaction is by using a conventional fission warhead. And so fusion bombs are obviously far more powerful than fission bombs, because you have two different nuclear reactions occurring at the same time. You have your fission reaction, which is then generating enough heat to cause your fusion reaction, which generates even more heat, and it all spirals out of control and everybody loses. Fun fact, plutonium-239 is the go-to for nuclear weapons. And so then, if a nuclear bomb is dropped, what types of radionuclides or radioactive particles are in the environment? Hundreds of different types, just because of the mechanism of action of a nuclear bomb. And, similar ones to that we see with a nuclear reactor, like cesium-137. However, there's hundreds more because of how rapid the reaction is compared to a fission reactor, which is generally very controlled and pretty slow, and so you have less radionuclides that result out afterwards because you've fully reacted, or 80% reacted the cores that are there. And these radioactive particles remain in the environment for years. Some can remain in the environment for 30 years, and then others, like uranium-235, have a half-life of 4 billion years. So it just depends on the type of radioactive particle you have. That being said, ladies and gentlemen, I hope you enjoyed today's episode. To summarize, we discussed a fission reactor, a fusion reactor, a fission bomb, and a fusion bomb. And the lessons from the past are simply we should invest in nuclear energy, but we should not invest in nuclear weapons. We should try as a species and come together to deproliferate nuclear weapons. However, that'll never happen, unfortunately, because nobody wins when you use a nuclear weapon. Now, what is a tactical nuclear weapon? A tactical nuclear weapon is one that has a very tiny nuclear warhead. So while it does generate radioactivity, it does not generate radioactivity on the citywide scale. It generates small amounts of radioactivity that can be targeted to a very relatively pinpoint area. So, you could use a tactical nuclear weapon to irradiate one bunker and not the city that the bunker is in. But once again, ladies and gentlemen, nuclear energy, particularly nuclear fusion, is not something to be scared of. It is, in my opinion, one of our tickets to a greener future. I hope you enjoyed today's episode, and if you have any questions or comments or suggestions for me and about the show, I'd love to hear them. Please let me know, and I hope you guys have a great weekend. I'll see you on Monday, and remember, as always, stand up and question everything.
Catch me if I fall.